This is the lesson number 19 example problem. It's the basic steel beam design using the LRFD method. It's the example we ran in class. Didn't quite get enough time to go through it in detail, so I thought I'd spend a few more minutes going through this example with you. I know it's remote, you've got to do it via presentation now, but I think by doing this it'll help you out and help you understand what's going on a little bit better. So the actual example that we want to go through is this steel beam structure that we've got here. And the beams themselves are B1, B2, B3, and B4, and you can see these over here on the actual structure here. B1 and B4, because they're the outside beams, they are not the critical beams. They only have a 6-foot tributary area, but beam 2 and B3 are the same. And so if we were to look at a tributary width of this guy right through here, we'd have 12 feet contributing to that area. And so the first thing we would have to do is take the distributed load acting in this area and convert it to an actual line load. And so if we were to do that, what we'd end up with is some load acting along the beam in this manner. The way we do that is back from the load tracing lesson, where we take our actual dead loads and live loads, multiply by that tributary width, and we determine the line load acting across that beam. So a couple other things to note on this problem right here before we get into the problem too far is that we're using 50 KSI steel, so it's a little bit higher strength steel, and we've also got a dead load of 100 pounds per square foot, a live load of 75 pounds per square foot. One other thing to note before we move on is that the bracing over here is on 6 foot on center. We're actually going to do a calculation at the end of the problem and see if that bracing is adequate in length to withstand the buckling level that we would need to. And so let's begin. To take that distributed area load and convert it to that distributed line load acting all the way along the beam, we first off take that 100 pounds per square foot, that's our dead load, multiply by the 12 feet tributary width, and we determine that we've got 1,200 pounds per foot of dead load acting along that beam. Same thing with the live load, 75 pounds per square foot, multiply that by the tributary width, and we've got 900 pounds per square foot. Now, the one thing that we do with LRFD that we haven't done thus far in the semester too much is use the factored loads. And so we've got to take and multiply all those factors. And we also have to consider different load combinations. We went through those. There's a whole bunch of those. Because I've only given you a dead load and a live load, we're going to consider only 2 cases. And those cases are 1.4 times the dead load, or 1.2 times the dead load plus 1.6 times the live load. And it's just pretty basic math from there. 1.4 times the dead load gives me 1,680 pounds per foot, considering that load case only. And if I do the other one, 1.2 times the dead load, this should be a plus sign right here, plus 1.6 times the live load of 900 pounds per foot. It actually shows that I've got 2,880 pounds per foot, which is the critical load combination. So this is the value that we want to use moving forward in this problem. You'll notice on this page right here, they've just taken the 2,880 pounds per foot and they've made it 2.88 kips per foot. Same number, they just divide by 1,000. And now they're showing the free body diagram of the beam here. So we've got the factored load up on top. And we can then determine our shear and our moment. You could do that by drawing the shear moment diagram, but typically what we do is we just use the common loading solutions and run with it from there. So the common load solution for maximum moment would be WL squared, W being the load, WL squared over 8. And again, just math, 2.88 kips per foot. The length of the beam is 24 feet. Square that, divide by 8. Note that my answer comes out in kip feet. A little bit later, we'll actually have to convert that back to kip inches. Do the same thing for shear. And so shear is WL over 2. And again, same numbers, plug them into the equation, and we determine that our shear is 34.6. Now, these are the maximum values that we determine based on our factored loads. And recall that what we want to do is compare our actual values to our resistance values. And we want to make sure that they're less. So we need to hang on to these 2 numbers right here. And as we go ahead and calculate what our factored resistance values are, we'll make sure that we fit within that basic definition that we've got over here on the side. The final thing that we want to do right here is once we've got our moment, now we can determine our plastic section modulus. And so plastic section modulus, if you recall, was that capital C value. This was that equation that we came up with in class. Recall that 12 right there is simply a value that is a conversion factor to convert this from kip feet to kip inches, so that when our math comes out in the end, we end up with inches cubed. And so plug in the value for our maximum moment, the actual moment that we determined. Recall that the bending factor is 0.9, and of course we're using 50 KSI still. Plug all that in your calculator, and we actually need a section modulus of 55.3 inches cubed. And anything less than that would be unacceptable. We wouldn't be able to actually handle those moments. Anything larger than that should be okay. So the next thing we want to do is go to our section modulus table, the plastic section modulus table, table A11. It's 2 different pages in your textbook, and you'll notice that on this table, the first column is the plastic section modulus. The values themselves are in decreasing order, and so it's really easy to quickly go in and determine where our section modulus fits within the table, and then pick some options off of that. Note, I'm on page 582 in the appendix, and you're able to find that table there. It actually starts on page 581 because there are bigger still sections on the previous page. And so I'm going to zoom in just a little bit now on this. So we see up here along the top, here's that same section modulus column right here, same descending order values right there. And we determined that we need 55.3. So anything smaller than that would be unacceptable. This W14 by 34, it just doesn't quite make it because the section modulus is too small. But anything larger than that, the 61.5, 64.0, 64.7, 66.5, you could continue on up the chain, and any of those beams are going to work. The problem is we get too far away from the 55.3, and we start to put more material in there than we need, and we price ourselves out of a job. So we got to stay practical in what we're using. So I'm going to look at these 4 values right here: a W18 by 35, a 12 by 45, 16 by 36, and a 14 by 38. And if we look at these 3 values, typically we will give you some parameter that says your constraint is using the lightest value. And so I'm simply going to compare the 35, 45, 36, 38. The 2 lightest are the 35 and the 36, but the W18 by 35 is a pound per foot lighter. Remember, the 35 is 35 pounds per foot. And so I'm actually going to select this beam as my member that I use going forward. Now, because I selected a W18 by 35, I've got all these other factors and parameters that come with that beam. They're simply the dimensions of the beam. Here's the area of the beam, 10.3 inches squared. The depth of the beam, meaning if my beam is over here, the depth of the beam would be the continual depth from top to bottom of the beam. The height of the H value there is the height of the webbing material. The width of the flange would be here, so the width of the beam. The thickness of the flange would be simply looking at that, so thickness of the flange. And then finally the thickness of the webbing. And so we've got all these parameters that we're able to gather from that, and we're able to move forward with the rest of our design. And so in the example in the textbook, you'll actually see that they've just pulled all of those values off of that table and show that's the one that I selected. And so now you can correlate where those values in the example come from with the table itself. The other thing I want to note out here to the side is that it shows this phi MP value. If MP is the largest moment that we're able to have, the largest plastic moment that is, this is when the plastic hinge develops, and of course it's factored because we've got that phi B right there, that 0.9. Note that they include this value right here, 249, and that's in kip feet. I'm actually going to show you how to calculate that. They do in the problem right there. So To figure out what the plastic moment is, we simply take the yield strength of the steel and multiply by the plastic section modulus. And so I've got the 50 kip inches squared. That should actually be 50 KSI, not 50 kip inches squared, I think. And then we've got the plastic section modulus on there. Convert it from inches to feet right there, and our answer comes out as 277 kip feet. And of course, then we need to multiply by the factor. You do that, and lo and behold, we actually get the same value that's in the table. So the textbook also says that in the example, this value can be found directly in table 11. A11B in the appendix. So that would be something that you could actually just simply pull from the table. You wouldn't necessarily have to calculate every time, but they do show you in the example how you could calculate that. So note that where it says phi MP, it's the plastic modulus here. This is the same as that phi MN that we described generically in the equation. And so we've now got that first value that we could compare. And recall that we're simply trying to determine if mu, the actual moment, is less than the factored resistance moment. And I've simply pulled the value straight out of the example previously, showing you those equations. And 207 is definitely less than 249. This step is not actually shown in the example simply because we picked a member big enough based on the necessary z. Meaning the section modulus there. In the process of picking a section modulus larger, we guaranteed ourselves that phi MP would automatically be bigger than our actual moment. And so you don't necessarily have to check this step. I just wanted to show you that in the process of doing this, we've actually determined that value does hold true from a design standpoint. Now, one thing the textbook does not do is add the weight of the beam back into the calculation. If you recall, all we had was the dead load and the live load that were acting on the beam itself. And so we do need to consider beam weight. Remember, it weighs 35 pounds per foot. And so we actually want to add that back in, make sure that we didn't exceed our moment based on that. And so here's the 35 pounds per foot. Remember, this is a dead load weight because it's weight of the beam, and we simply multiply that by 1.2 because we've got to do the factored load. And so the total load right there ends up being 42 pounds per foot. Additional factored load based on beam weight. That's for a W18 by 35. To find out the additional moment that is caused by this 42 pounds per foot of additional load, we simply recalculate our moment value, including that 42 pounds per foot. Note I've converted it to kips per foot right here. And I end up with 3 kip feet in the end. We initially had 207 from our dead load and live load above the structure. And so we end up with 210 kip feet. And that still is less than the factored load that we had, and so we're acceptable right there with the addition of the beam. Again, as when we talked about timber, if you're right on the border and then you add in the beam weight, oftentimes you'll exceed it. But if your beam is quite a ways away, usually you're okay. But you should always check that weight. We'll do the same thing with the shear value. Same calculation for shear. Comes from our common shape solution. The additional beam weight causes a half kip additional shear. Simply add that there. We actually haven't done the shear calculations here, but this is the value that we're going to compare with moving forward. 35.1 kips of total shear result from the dead load and live load acting above the beam, as well as the beam weight in there. And because we've done bending first, oftentimes shear is okay, but we do need to actually check that. So if you recall, we also need to check and make sure this beam is a compact section. Compact section simply means that the beam is capable of, the steel beam is capable of failing in a plastic hinge. And so we need to check the compactness of the actual flange portion of the beam, and that's determined simply by doing the ratio of the width of the flange to 2 times the thickness of the flange. And then we also need to check the webbing compactness, and that's simply the height of the web to the thickness of the web. These are the values that were pulled out of that table A11, simply the dimensions of the beam. We plug them in there, and then we make sure that they are less than the allowable values for A50 still, the 50 KSI still. And so you do the math right there. We determine that 7.06 is less than 9.09. The flange is okay. You also check the web. 51.7 is less than 90.5. The web is compact. If they aren't compact, it doesn't necessarily mean that your beam is going to not work. It simply means that the beam will not fail in a plastic hinge. Now let's check our shear value here. Recall that basically we want to take the ratio of the height of the webbing to the thickness of the webbing. And we want to compare that against 418 over the square root of Fy. But we also want to compare that with 523 over the square root of Fy. Note, I was having a hard time finding a square root sign, and so I've just notated Fy to the 0.5 to mean the same thing here. And recall that if I am less than 418 over square root of Fy, then I'm case 1, and that gives me a certain equation that I can use. And that equation is actually shown here on this example. If I'm greater than 523 over the square root of Fy, then I'm actually case 3. That was a different equation that we put on the board. And if I'm somewhere in the middle right here, that brings up case 2, and that would be a different equation. And so for this particular example right here, one other thing to note here, in the example, I have 0.6 times the yield strength times the area of the webbing. And this is how we notated it on the board in class. But the area of the webbing is simply the thickness of the webbing times the total depth of the beam. That's that approximate value we looked at. So they run the math right here. They end up with, note that everything's in inches as they plug the math in. They determine that 51.7 is less than 59, which was 418 over the square root of 50 KSI. Note that this is 50 KSI, not 50,000 PSI in the equation here. And because 51.7 is less than 59, we're this situation right here, and we're case 1. And so we simply need to come back up to this equation up here and plug our numbers in and see if our shear values hold true. So here is the V sub n equation that you see above. Here is the factor for V. Remember, we're calculating the ultimate shear value and then reducing it slightly by a factor. And they determine that that factored shear value has to be 143.4. And recall that we were comparing 35.1 was the actual applied shear that we came up with. And so we're simply able to compare those two values. I show it down here again. Recall that VU needs to be less than the factored value, and so 35.1 is less than the 143.4. We're okay. Again, this comes back from the fact that we did the beam bending first. Bending usually governs, and we're simply checking shear to make sure shear is okay. It usually will be. The thing that makes shear slightly more complicated with LRFD and with steel design is the fact that you have to utilize one of 3 different cases for the shear value. Depending on the shape of the beam, the shear will behave differently as it transfers across the cross section. So we're done with checking shear. The next thing we want to do is check shear. Oh, sorry. We've checked bending, we've checked shear. The next thing we want to do is check deflection. As indicated in class, the one trick to checking deflection is that we don't actually want to use our factored loads anymore. If we use factored loads, what we're saying is our beam is actually going to deflect more because we're using these theoretically bigger loads. But we really want to look at what's actually going to happen from a deflection standpoint, and just make sure we're within our tolerances. So use the actual service loads, meaning the actual loads that are applied. So here's I believe this is the dead load the 1,200 pounds per foot. Here's the live load, 900 pounds per foot. And then we also need to account for the beam weight. Add those three together and we come up with 2,135 pounds per foot as a load that we need to apply in this situation. In our deflection equation, we are going to use a distributed line load, which is usually what we're going to use with beam design. If you had a concentrated load, you might have to split this into two pieces as we did with timber design. But because we simply have a distributed load, we can get away with just the one equation here. And recall that for a distributed load, you can find these on the common load solutions. 5/384 times WL fourth divided by EI would be the equation here. We need to determine what the moment of inertia is and what the modulus of elasticity is. Sorry, I pointed those backwards. But modulus of elasticity and moment of inertia, so that we can plug those in. And so modulus of elasticity for steel, if we pull that from table 5.2 in your textbook, table 5.2 lists this as 30,000 KSI. Occasionally you'll see some tables will have this as 29,000 KSI. I believe your textbook shows A36 still as 29, and they increase it to 30,000 for 50 KSI steel. You go ahead and use whatever's in the table there. It doesn't change the number by that much by doing that. You use the 30,000 KSI that you pull from the table. Moment of inertia, because this is a common shape, it's a shape, a steel beam that's produced in industry. We're able to quickly grab the moment of inertia from a table. Actually got to go to table A3 to find that value. I'm not going to go there and show you that, but you can get this value for, I think it was a W18 by 35. Look up the moment of inertia for that and you should come up with 510 inches to the fourth. We've got everything we need now to plug into our deflection equation here. Here's our 21.35 pounds per foot, 24 feet to the fourth. That's the L to the fourth. Remember that this foot right here cancels with one of these feet, and that leaves me with a feet cubed. Go ahead and do 24 to the fourth. I'm showing the units as they cancel here. But the final thing we need to do is convert all that to inches, and so we've got this extra 12 inches per foot to the cubed. And so 12 to the cubed also needs to be included up there on the top. Down here in the bottom, because I included this in pounds per foot right here, meaning the load, I'm going to put the modulus of elasticity down here in PSI, and so I get 30 million PSI, and finally 510 inches to the fourth. Do the math through that whole thing and I come up with 1.04 inches. So this whole beam is going to deflect 1.04 inches at the maximum, which occurs at the center. What's the tolerance? Because we're looking at a dead load and a live load situation, the tolerance would be this L over 240. And so to calculate the delta allowable, simply take the length of the beam and of course convert it to inches, divide by 240, and we can actually tolerate 1.2 inches. So we compare those two values, and sorry, I'm missing some of my things I built in. But we compare those two values right here. 1.04 is less than the 1.02. We're within our acceptable tolerance, and deflection is okay. Final thing we need to check on this problem, and then the problem is done. We need to check our unbraced length. The unbraced length is found using this equation right here. This simply means the unbraced length for a plastic hinge failure. 300 times the radius of gyration, this is r sub y right here, and we divide that by the square root of the yield strength. So square root of 50, meaning 50 KSI. We need to find the radius of gyration. It comes from the same table that we found the moment of inertia in, table A3. For a W18 by 35, the radius of gyration is 1.22 inches. Once you've got the value, it's really easy to do the math, and we determine that the unbraced length, meaning the minimum length, the maximum length that we can handle without any bracing is 51.8 inches if we're going to achieve a plastic failure. I convert that to feet, it's 4.3 feet. And recall at the very first of the problem, they actually braced it every 6 feet. And so they actually didn't brace this problem sufficiently to meet this true plastic hinge failure. That doesn't mean that the beam is not going to work. It just means the beam is not being as efficient as it could when it comes to the plastic hinge failure mechanism. And so the final thing that I show on this problem is we need spacing of at least 4.3 feet. Let's use a practical spacing. If this beam is 24 feet long, I'm going to brace it every 4 feet. And we'll call that right there the length of my bracing. That is the final step in this problem. You've gone through the problem. You started out by looking at bending and making sure bending was okay. And in the process of doing that, you actually selected a beam size. From there, you simply made sure the beam was compact. You checked the shear. You checked the deflection. And then we finally checked the unbraced length and determined that. Those are the 4 or 5 basic steps that go into beam design. I hope this will help re-explain just a little bit what the problem is all about. If there was anything in the problem, I'm hoping that this little explanation will help walk you through maybe where some of the numbers came from and what they mean. So, thanks for listening.